we are. When I spread its light out into a rainbow, all of the colors are there. So the thing we don't understand yet is why the rainbow from the sun is missing certain colors. Right? Here I've got everything. But when I do this with the sun in detail, I notice that some colors are missing. So that's our task for the next 2 days. Why is it that when I do that with the sun, sorry, I got to fix the camera angle after that. There we go. Let's see, I want to do, we'll fix that in a minute. Sorry folks, every time I change stuff I have to do a little bit of twiddling. That when I do that for the sun, colors are absent in the rainbow. That's our challenge. Before we talk more about that, though, I'd like to make some announcements, as we always do. If you haven't submitted Project 3 yet, that was nominally due yesterday, so you need to do that very, very soon. I got a lot of questions from students who said, why didn't one of the simulators work? There's something missing here. That was my fault when I was making your slides. But the reason it didn't work is because folks didn't read the directions. So let me show you what I mean here. So if we go to the binary star simulator, and here I'm going to just get Zoom chat out of the way. Zoom chat is too big, so we want to make Zoom chat smaller and someplace else, like that. Now let's make this full screen. Make the code bigger. So let me reset this. Many of you, yes, I'm sure, just do the thing. Many of you, when you hit play here, you saw this error message down at the bottom. Cannot multiply string by something that is not a number. This thing you see printed at the bottom in red. So many of you said, oh, well, something's broken. Let me post on Piazza or email me or so on. And I answered a bunch of people's messages like that. I wasn't able to answer them all. But if you look at the text in the project, the text says, well, in this code, not everything is filled in for you. And you will need to, where'd it go? You will need to fill in the missing bits yourself. There we are. So notice that there are no numbers here for the starting distance of the planet, its velocity, or its mass on lines 5, 6, and 7. And when you hit play, nothing happens because the code has a bug. And this red is the thing saying, I don't know how to multiply nothing by a number. But if you put in some values, starting distance for the planet, let's say, 0.8 AU. Starting velocity, let's make it go at 6 AU per year, and let's give it a mass. Let's give it the same mass as Jupiter. So this is a Jupiter-like planet, that's where Venus is. And if I do this, then the simulator does what you expect. It simulates. Now, the point of this project, the thing that we want you to think through, is why is it that in this case, this planet doesn't retrace its same orbit, right? Notice that it's going around in a circle, or in an ellipse, but that ellipse doesn't repeat its own path. That somehow the fact that when I have binary stars in the middle, that makes its orbit precess. So that's kind of what Project 3 was involving you thinking through. So if there are any more questions about Project 3, come to help hours tomorrow. We're going to have a couple of those tomorrow. Tomorrow morning, I'll tell you how that works in a minute. Post questions on Piazza and get Project 3 in as soon as you can. So let's get rid of these orbiting stars. Let me go back to my slides. Let's see, I need to push this button here, and then this button, and then that. Educational Porpoises says, when I flipped back to the spectrum, that there are more dark lines in the blue than dark lines in the red. That's interesting. It is a curious phenomenon that there are more of these dark lines down here in the shorter wavelength range than in the longer wavelength range up there. I have a suspicion of why that may be true. And so Orange Sauce Man asked that question again on Sunday, and I can give you a more in-depth answer. We got a couple of other questions in Zoom chat. Allison asks, if we haven't filled out the survey to participate in the peer review program, yes, you can still do that. So that survey is on Blackboard. It's under assignments on Blackboard. So just go to Blackboard, click on assignments, and there's an option for, would you like to do the peer review thing, yes or no? Remember, for your papers, if you do participate in peer review, your drafts should be turned in tomorrow. We will tell you who that is. Tomorrow we will send out a list of who you should send your draft to. So what I'm going to do is tonight I'm going to go look at Blackboard and go look at the list of everybody who said, yes, I would like to give and receive feedback, and then match you up with each other. And then you'll get a note tomorrow saying, here's who you're matched with. And then you will have until November 1st to provide that feedback, get feedback yourself, and act on that feedback to submit your final draft. Marco asks, we emailed 2 of our labs to the wrong place, and 2 weeks ago we sent them to the right place. We have not updated those grades on Blackboard yet. We're doing that in a spreadsheet internally. We are going to do another Blackboard update tomorrow. Tyler, so let me talk about office hours today. So there is a seminar I need to be at on Thursday, so after this class. But I can multitask a little bit, so I will be answering Piazza questions off and on from 4 to 5 today. So if you have questions for me, post them on Piazza, but I won't be able to be on Zoom because I have to be somewhere else on Zoom. Luke, if you're not participating in the peer review program, the final draft is due next week. I had originally posted the 26th, but we will push that back to the 28th, which I believe is Wednesday. So turn your drafts in next week. LMCG asks something really important. Are we meeting at our normal time on Sunday? Yes. Remember, we have classes on the weekend this week. This Sunday, you will go to all of your Thursday classes, my class and anybody else's, but not lab. But here's the catch. I will not be able to be here on Sunday. I really apologize for that. But this time on Sunday, I have to be somewhere else. What that means is you can either come at 12:30. So at 12:30, we'll be doing the same thing where I always teach 2 of these. So you can either come at 12:30, or you can watch the recording on Twitch. We'll post the one on YouTube right away. I know I'm behind on YouTube links. I am so sorry. You can either grab it right off Twitch, or you can watch it on YouTube at 2 o'clock. So I'm really sorry, I cannot be here at that time. So you can just grab that recording and watch it, or you can come to the 12:30 class, and it'll probably be more fun. The 12:30 class goes until 1:50, Porpoise. Project 4 I will post tomorrow. In it, you and your group will look at some exam questions from last year and kind of make a study guide. So that one will go live tomorrow. And we had a bit of confusion about the midterm evaluation thing, and I finally realized what happened. The university is doing a midterm course evaluation thing, and you got a bunch of messages about that, and some people were asking me about it, and I thought that's what everybody meant. But on the syllabus, I had listed October 15th as a date for evaluating each other in your groups, where basically you will tell me if the people in your groups are working well with you. And I had thought everybody was asking me about the university thing, but it turns out that some of the questions are about the thing on the syllabus. And so I am sorry, I misinterpreted some of those questions as about the university's midterm evaluation. The thing on the syllabus, you'll probably say, oh, that didn't happen. Well, since we started the group work a little bit late, we're postponing that until next week. But next week, we will contact you and basically ask you to tell us if the people in your group were working well with you. You will get a grade for doing that, and you will also get a grade based on whether you have been working well with your groups. We have two sorts of help hours tomorrow. So as I've mentioned, sometimes I have boring meetings on Friday mornings. I would much rather be with you all, but I'm going to be stuck in a Zoom call with the dean, wishing I was literally anywhere else, because these meetings consist of rubber stamping paperwork. So 8 a.m. to 9:15, I'll be on the steps of Hendrix. I've got my break for a boring meeting, and then I'll be back at noon to 1:30 tomorrow. And you can ask me, of course, anything you like. I'll be on Zoom, and I'll be on the steps of Hendrix. But also tomorrow, Lisa Lee, one of our coaches, has offered to help people with their papers. And she, both Friday and Saturday, will be on Zoom 10:30 to 2. She's going to be using her own Zoom rooms to do this. I'll send you if I put the links up on the slides, then that's going to be a mess. So I will post those links on Blackboard and send them to everyone by email. I'll post them also on the course website. So if you're wanting to go to have Lisa help you with your papers, then show up to Zoom either Friday or Saturday. And she can help you with anything else as well. She's, she's very good at this. Are there any other questions people have about logistical stuff before we talk about one more thing? Okay, I have alluded a couple of times this semester to a final project for this class. We're going to make the more formal presentation of it next week. The page on the website is not quite ready to go for it. But I wanted to give you all a description of the assignment now and give you a little bit of lead time so you can think about what you'd like to do. This is the last thing you'll need to do for our class. It is due somewhere between December 5 and December 10 will be the due date. We're finalizing that. We'll post it next week. And this is the thing that most people find the most fun in this class. It is an opportunity for you to connect astronomy, to connect astrophysics with, or to connect science more generally with something else you're passionate about or something else you study. Many people choose to write papers that connect the stuff of science to the stuff of the rest of their studies or the rest of their life. But not everyone does papers. In the past, we have had people do things, possibly the strangest was we had someone design a font, where every character in the font represented something astronomical in a really clever way, like taught Kepler's laws and stuff like that. And it was really, really cool. We had someone last year who was a religion major, who was interested in European paganism, make a tarot deck. And everything in the tarot deck, all of the major arcana, were astronomical ideas, and she had a really clever way of basically teaching the way tarot works through the story of humanity's engagement with the stars. I learned a lot from that one. We've had people write poetry. We've had people write screenplays. We had a couple of people do a screenplay, like actually act. We had some people from the marching band do a marching band show of Kepler's laws. You know, somebody in the middle was the sun, and other people were running around them and going faster when they were closer and stuff like that. We had, what are some of the other more creative ones? We had somebody make a video game a couple of years ago with one of those little like online video game makers that was pretty clever. We've had people write and perform music. We've had people make art. We had someone do a painting that was a reimagining of Van Gogh's Starry Night. We've been doing this for some years, and people, like every year, students come up with really awesome, amazing things. I have made on the course website, let me see if I can get to it. It's not up yet, you can't click on it yet, but it will be soon. A page that kind of presents the assignment and some of the prompts. And I want to comment on that now. We'll make me smaller so you can read better. There we go. Oh, no, I clicked the wrong thing. Ack. Let's see, I have to click this, then I have to make me smaller, and then I have to click that. There we go. Well, we got to put the Zoom chat back where it goes. Back up here. Actually, we'll just get rid of Zoom chat for the time being, just so you can read. There we go. So this project is, you know, as I've said here, it's a chance for you to bring something of yourself to the class. Because you all are, many of you, are not going to be professional scientists, not going to be professional engineers. You're going to do other things that are more important. You're going to be politicians. You're going to be culture leaders. You're going to be artists. You're going to be storytellers. And I would like for you to get some experience mixing the stuff of science and mixing the stuff of astronomy with all of these other things in your life that you are passionate about and that you'll do. And I'd like you to have an opportunity to take those other skills you have and use those as lenses to look at science and astronomy with. I've given you a bunch of prompts on this webpage. Again, a link will appear after this class. I'm going to push the button on the website that makes this go live. And you can, I've suggested a few things, I've mentioned some other things, but you can pick pretty much anything that sounds cool. The only requirements are that it connect science or science fiction or astronomy or the process of science to another intellectual pursuit of yours, whether it's art or policy or history or writing or fiction or whatever. So this piece of the assignment, if you do something artistic, we would like you to also write an artist statement, basically telling us about the science underlying the artistic thing you have done. I'll talk more about this next week, but I've written a lot of prompts here. They're just intended to give you ideas, to give you, you can do them, of course. Or you can say, oh, well, I want to do this instead. This is an opportunity for you to have a lot of fun. Irene Daga asks in Twitch chat, can we write film reviews about science fiction movies? Absolutely. That's the kind of thing we have in mind. And in fact, one of these is, like the two that you see above you that I've scrolled down to, are explicitly film reviews about Star Wars and Star Trek, but people have done other films. Like, we've got a really good one about Arrival. We've gotten some about Interstellar. So if there's a piece of science fiction that you're very, very curious about, very, a fan of, then tell us about it. Tell us how this work of science fiction blends ways that the universe really works with fiction to tell a better story. Yeah, if you want to do 2001 Space Odyssey, yeah, that could be a great final project. Some of them are, very, very nerdy. There's one about one of the Star Wars books that was actually written by a physicist, Timothy Zahn. There's one about the three-body problem that's related to the project that you have done. But I've tried to come up with things that touch on many of the different majors that Syracuse offers. And even though this link is not formally live yet on the website, I'm going to go ahead and post it in chat, in Zoom chat, so people can look at it. If you want to just click through and read through the prompts. I'll post it as soon as class is over. So does anybody else have something that they are pondering that might be a good idea for this that they'd like to type in chat? Luke proposed a stand-up comedy set about science. That sounds awesome. One of the best that we've gotten, and I say best in that it made us laugh our asses off grading it, was someone had done a rap battle between Ptolemy, Kepler, Copernicus, Galileo, Newton, and the Pope, I think, the one that like put Galileo in prison. I think that's right. They wrote a rap battle about all of these figures in the development of the model of the solar system, and it was flippin' hilarious. Alana says, paint the night sky and embroider where the stars were on the night when I was born. Like the phase of the moon and all that. That sounds beautiful, Alana. And Alana, if you do that, that sounds amazing. If you do that, might I suggest that you give it to your mother as a gift? She will treasure that for her whole life. Michael has suggested doing a variant on Van Gogh's Starry Night. Yeah, we've had other people look at that. Yeah, Elena, like that kind of thing, that sort of sentimental human aspect that is what this project is designed to encourage, is for you to connect the scientific to the human, because really they're the same thing. Arian, this is due, it's going to be sometime between the 5th and the 10th of December. So you have lots of time. LMCG has said how physics has changed the way we think about baseball. Sure, if you want to write about the physics of baseball, that's fine. Anything else anyone wants to propose? You have time. We'll talk more about this next week. All right, so that's all I've wanted to say about announcements. Now let's talk about light. Okay, there are a few more questions. Do you need to get approval on an idea not listed before you do it? We will have a process for you to submit a proposal, for you to say, here is a thing I would like to do. and we can give you advice on how to make it even better. In all of the years we've been doing this, I don't think we have ever said, that is a sucky idea, it's a terrible thing. We pretty much anything you come up with that involves a depth of intellectual effort and thinking deeply is brilliant. Porpoise, you've said trying to figure out where to start. Yeah, this is the most open-ended assignment that you will likely ever have. It is an opportunity for you to this is what I want you to remember from this class. I want you to, like the details about Kepler's laws and how orbits work, if you forget those things in 5 years, I don't mind, right? That's not what this class is about. But what I'd like you to take away from this class is that the universe is beautiful, that it's inspiring, that the scientific method is a powerful and humbling thing, that we can understand how the universe works, we can understand our place in it, and those things are often the basis of us getting the inspiration to better our own condition. And if you take that from our class, and if you find something to do for your final project that reminds you of that, then I don't care anything else that's happened this semester. That's what I want. Could you, Real Short King, could you track Polaris in Stellarium over 100,000 years? Yes. So Real Short King has said, let me now dig into this idea of the precession of the equinoxes, the idea that Polaris will not always be the North Star. And if what you want to do is to investigate changes over tens of thousands of years, thousands and tens of thousands of years in Stellarium, that's brilliant. That will lead you to questions like, why is my horoscope wrong? How does the North Star change? How does Earth's orbit make that happen? And if you want to investigate that, that's great. All right. So, as we saw before, things with a temperature produce light of a continuous band of wavelengths. So you saw that when I turned on this thing, right, this produces all of the colors of the rainbow. If I stick this diffraction grating in front of it, so it is currently keying, right? We don't want it to do that. So, boop. When I put this here, this produces all of the colors of the rainbow. Because this is just a very, very, very hot object. But we saw last time that we can produce light in other ways too. And as an example, I'd like to use this. What is this? I'm going to go turn the lights off in the room, but in the meantime, tell me what you're looking at. What is this object? What is this machine? It is a meme, as Henshi points out. It's a lamp. Educational Porpoises has said it's like a neon light, but they're not sure what gas this is. Yeah, so this is in fact neon. So this is actually a neon light. It is not a spectrometer. It is a thing we're going to point a spectrometer at. So this, where'd the other one go? It's on the other side of the table, of course. You can't see it, but the thing I'm about to put in front of the camera separates light into its component colors. So let's put the neon lamp all the way over on this side. And then when I do this, you see over on the left the various colors that this light is made of. Porpoise said they're not sure what color or what chemical this is. This one is in fact neon. But I don't have to use neon. I could put in other tubes with other gases. This one's xenon. Again, you're going to put the diffraction grating in front of the camera. Whoop. It's deciding whether it wants to be in focus or not. We'll help it. We're going to make this brighter and put it a little bit closer to the center of the frame so the camera will have an easier time locking focus. And now you see another set of lines. Some of them only have a few lines, like this one. This one's hydrogen. Here you can only see 3 lines. A red one, a blue one, and a purple one. So what's going on here? So our goal for today is to understand how this works and why, instead of getting an entire rainbow like you got for the incandescent light that's just hot, you got a few thin, bright lines. I've got to reset some stuff on the camera. Hit this button, and then I got to turn this thing so I'm less tall. So we're going to have to understand some chemistry to do this. Too dark. There we go. And to do this, the specific idea we need from chemistry is that electrons in atoms have only very specific energy levels. We measure their energies in units called electron volts. It's just an amount of energy. Normally in atoms, the electrons hang out at the bottom energy levels called the ground state. And as you put in more electrons, they fill up from the bottom up. And this process of filling up energy levels in atoms is what leads to the periodic table. This was kind of the first great revelation of quantum mechanics. And more about this process is your intro chemistry class. This one day of chemistry does not replace your intro chemistry class in your transcript. Now, I've got a bunch more slides that I could do a clicky-clicky through. Right, they've got some questions on them, but we're not going to go through them today because these slides are mostly here for people who are reviewing. Instead, I want to talk through this on the blackboard. So if you'll just give me just 1 minute, we're going to switch to a camera set up on the blackboard. We're going to make the green screen go away. There's stuff still on the blackboard from last time, which I will erase. So remember, our goal here is to understand sunlight. Let me fix the camera just so it's framing the blackboard like it should be. our goal is to understand sunlight. And we know from quantum mechanics that there's a connection between the energy of a photon and its color. And what we're going to see, the spoiler here, is that what we will see is that the energy levels of atoms are connected to the colors of light that they produce and absorb. So first, we need our spectrum. So I'm going to draw it over here in the corner of the board. I'm going to talk for a bit as I draw. It doesn't need to be that tall. The spectra that you saw earlier, right, when I did this with the camera, were horizontal, but this one I will draw vertical. The visible range goes from 3.2 eV to 1.6 eV. So these are the highest energy photons that our eyeballs can see, and these are the lowest energy photons. Which one's red and which one's blue? I'd like to do a lot of these things as a dialogue. So this is going to be the rainbow of the visible spectrum, but do I draw the red end on top or the red end on bottom? Now I'm going to collect all the colors of chalk I need to do this. Erica says red goes on the top and blue goes on the bottom. Porpoise has said the other way around, red on the bottom, blue on the top. So which way is it? Where do those things come from? Well, this is the energy of a photon, right? And what do you know about photons with high or low energy? You know that high energy, photons with a lot of energy, have short wavelengths. As Porpoise has said, blue is shorter wavelength. Shorter wavelength means higher frequency, which means higher energy. So yeah, this is blue. And this is red. What colors are up here off of the top? What happens when I go beyond 3.2? And also, what happens down here? Well, yeah, energy that's past the blue side of what I can see is ultraviolet. I don't have any purple chalk. So we're not going to get the whole rainbow. And down here is infrared. So I'm now going to color this in. Let's see. So we've got some dull red down here, which fades into some brighter red. Quite a lot of red on the spectrum, actually, which then leads to orange. I'm doing this quickly because I'm doing it in real time with you all, which then blends into yellow. Green. This is just approximate, so don't quote me on these divisions. And then finally blue. So this is the best I can do in just a few minutes. We will come back to this later. And this is the kind of spectrum that you would expect from a hot object. And we saw with the incandescent light bulb that I'm going to try to hold up here if I get enough hands. This guy, the incandescent light bulb, this just heats this thing up. This is an electric power source, and this just makes this hot. And that produces all of the colors of the rainbow. So this is the sort of spectrum you would get from a hot object. We'll label this here. It's a continuous spectrum which is all colors like you'd get from a hot object. But our task was not to understand this, it's to understand the neon light that only makes a few colors. And to do that, we've got to go back to chemistry. So I'm going to draw energy levels for an atom. This is not a real element. This is an element we're just making up for the purposes of demonstration. I want to show you how this goes. How do we label energy levels? Bringing my colors of chalk back to the other side of the board. We label them with the letter lowercase n, starting from the bottom. N equals 1 here, the lowest energy level is called the ground state. Like, the ground is the lowest thing. And each energy level has a certain amount of energy. So the ground state has 0 electron volts. The n equals 2 state, again, we're just going to make up some numbers here. We'll give it 5 electron volts. The n equals 3 state, we'll say, we're just making up numbers, has 8 electron volts, and the n equals 4 has 10. So this is a diagram, an energy level diagram of a hypothetical element that we have made up. We've got a couple of questions from Twitch chat from folks who have taken chemistry. Porpoise has said, how precisely are we labeling? Not sure if we're dealing with s or p orbitals, things like that. The short version is that it doesn't really matter whether, so yes, I could say, well, if this is n equals 2, is this n equals to s or is this 2p? It turns out not to matter. That hydrogen, so here I'm speaking to the people who've taken chemistry before. In hydrogen, it turns out that the s and the p and the d and the f orbitals have very, 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 very nearly the same energy. Other atoms, that's not the case. As Porpoise says, there is a slight difference. So really, in other elements, in real elements, you have other lines in here. This structure that I've drawn on the board, you might have something like this. Real atoms have lots and lots of lines. Lots and lots of energy levels that are indexed not just by the number n, but by other things as well. And you can read about fine structure and hyperfine structure, and pretty soon you'll find it really cool and say, hey, I'll be a physics major. But if you don't want to do that, it's not really relevant to our story, because all that matters for our story is that we can know what these energy levels are, and that they are specific to each kind of atom. That's important. We'll call this one, well, this is an element we made up in the basement of Syracuse University, so we'll call this Syracusan. So now let's think about what the electrons in it can do. suppose I have an electron, we'll draw them in, we'll use yellow. If I've got an electron down here at the bottom, in the ground state, I left on an extra line, thank you. Thank you, Porpoise. How can I get this electron up here to the n equals 2 level? I can't just like do that. Why not? I'd have to heat it up, as Ethan says. I'd have to give it energy. Yeah, if I'm going to move an electron up, this is a gain of energy. So I've got to put 5 eV of energy in somehow. I can do this with heat in some circumstances. I can do it with a chemical reaction. I can do it with an electric current. But one way to do it is with light. So to do this, I could put in a 5 eV photon. What would happen if I put in an 8 eV photon? Well, that's a jump of 8, so I could put in an 8 eV photon to get all the way up there. What if I have an electron in the ground state and I hit it with a 7 eV photon? So here's our electron again, they're all yellow. What happens if I put in a 7 eV photon? Will any of these electrons absorb that 7 eV photon and jump up to a higher energy level? Michael has said, does it stay at n equals 2? Porpoise has proposed that, okay, it jumps up to n equals 2, and the other 2 eV of energy are re-released immediately. So one thing that you might say, so here's a big question mark. I could imagine this happening. I could imagine jumping all the way up to, up to n equals 2, this being absorbed, and then giving off the extra 2 eV as like change, right? You go buy a bagel, you give the person at People's Place a $5 bill, and they say your bagel was $2, so we'll give you $3 back, right? You pay the atom 7 electron volts, the bagel cost 5 electron volts, and you get 2 electron volts back as change, right? But this is totally reasonable. It conserves energy. It's something you could imagine happening, but it doesn't work like this. We had no way of knowing that, right? We just had to do experiments. Benjamin says, I've forgotten the tip, yeah. Nature doesn't make change. So it turns out that this 7 eV photon is not absorbed at all. It just passes right on through, and the atom ignores it. For whatever reason, quantum mechanics is an exact change-only business. So now we understand how atoms absorb light. An atom can absorb light, absorb a photon, and gain energy. So let's write that down. But what happens if the electron is already at a higher energy level? What happens if I've got a bunch of electrons up here? It doesn't really matter how they got up there, but for our purposes, let's say they were excited up there by an electric current. So they want to go back down to the ground state. How do they get there? You might imagine that this is many atoms of Syracusium. Yeah, as Ethan says, they release energy as light. So let's make this a bit exact. Where can this electron go? To n equals 3, yeah. So this one could transition down to n equals 3 and produce. We'll just draw, continue with our wiggly lines. We'll do these wiggly lines in red and produce. So what's the energy of this photon? Two eV, as Michael and Porpoise have said, because it's lost 2 eV of energy, so that's what comes out. Let's write this down too. An atom can jump to a lower energy level by emitting a photon with energy equal to the difference. So we got 2 eV out of here. But what other jumps can I get? Ethan has said, oh, Ethan has figured the whole thing out. The higher energy releases are the bluer lines. Exactly. Ethan, you have figured out the whole thing. Yes. I can make this jump. I can make this jump. I can make that jump. And each of those possible jumps corresponds to a different photon energy. It's different line in the spectrum. So, and we're going to work all of that out in just a moment. So here, this one, let's see, that would be 5 eV. And that one's 10. Now, I'm out of Blackboard at this point, so I'm going to have to erase this, but we remember how it works, because I want to make a list of all of the jumps this atom can do. Let's see, what have I done? I've gone from 4 to 3, and that emits a photon of 2 eV. I can go from 4 to 2, And that emits a photon of 5 eV. 4 to 1, that's 10 eV. But what else happens? And Porpoise has started comparing them to here. So yes, that's the next step, right? 4 to 3 is 2 electron volts, so that's a certain color. They haven't said that one. They've said that 4 to 2 is outside the visible spectrum. This is the next step. So this one is ultraviolet. 4 to 1 is very definitely ultraviolet. And Porpoise has told me that the remaining releases are 3 to 2, 3 to 1, and 2 to 1. So let me draw those as well. Because I've also got this jump, this jump, and I could do that one. So every possible combination of energy levels is something that can happen as these atoms make their way back down to the ground state. So let's see. This one here, let's see, 8 minus 5 is 3. So that's 3 eV. 10 minus 5 is 5. I'm just drawing them at random angles. And do I have them all? Yes, I don't have this one. So every possible jump produces a photon of a specific energy. Porpoise says I already did 4 to 2. Yes, I already did 4 to 2. All right. That one is indeed a duplicate. When you do this, you've got to make sure you don't double count. And that's why this sort of table can be helpful. So 3 to 2. Let's see, 3 to 2 was 3 eV. Three to 1 is 8 eV. And 2 to 1 is 5 eV. We've already seen that these two are ultraviolet. That one's 5. That's also ultraviolet. The 8 one is going to be UV as well. These have energies greater than 3.2. You skipped 3 to, yeah, I did skip 3 to 1, thank you. Yeah, so 3 down to 1. It's easy to mess this up, right? It's easy to forget stuff, especially when you're talking at the same time. So 8 down to 0 is 8 eV. Now my chart's ready. So all of these are greater than the top end of the visible spectrum, so we can't see them. But what about 2 and 3 electron volts? Where are those going to be on our spectrum? Two and 3 are visible light, yeah. So which are they going to be? So 3 eV, as Twitch chat tells us, 3 eV is close to the top, right? So 3 eV is going to be here. And 2 eV, well, that's closer to this side, so this is going to be here. So this is orange, and 3eV is blue. Hey, what do you know? Syracusium glows orange and blue. That was a happy accident. I did not intend for it to come out that way, but it did. So this fake chemical element we just invented, called syracusium, when I run an electric current through it, like I did in my little neon light thinger, which I'm trying to get into the frame, this thing, it's tied to power, it glows orange and blue. And if you were to look at its spectrum through a diffraction grating, you would see an orange line and a blue line. So I'd like to pause now. Are there any questions that anybody has about what we've just done? So what we've got now one more thing I want to say before I erase that. Let me draw this. So as a reminder, so this object is a hot thing. So any hot object produces all of the colors of the rainbow if it is at the right temperature. So something that is cold, like a person at a few hundred Kelvin, produces infrared, but something that is a few thousand degrees, like a star, produces all of the colors of the rainbow in a continuous spectrum. We shouldn't have these single bright lines here. Tyler in Zoom chat says, I'm confused, I'm not sure how you calculated the energies. So those energies that we calculated are the differences between the energy levels. So let me erase all of the extra trash. Actually, let me just draw it again. So here are our energy levels. The top one was n equals 4 with 10 eV. The next one was n equals 3 with 8 eV. N equals 2 had 5 eV. And the ground state n equals 1 had 0. And the energies that this thing emits are just the differences between the energy levels. So for instance, going from 4 to 3, this gap here is 2 electron volts. So when an electron makes this jump downwards, it emits a photon of 2 eV. Not left-handed. There we go. Whoop, it's off the camera. Sorry about that. Yeah, good. So thank you, Tyler, so much for asking that question. This is like probably the last highly technical thing we will do. It's not that technical, but this is the last, kind of number crunchy thing we will do in class. So thank you so much for asking the clarification questions. The math is just arithmetic, but it's which numbers you subtract are important. So what we saw then is if I put a tube of syracusium in my little box, it will produce a spectrum that has just 2 lines in it. One line up here, and one line here. Along with lines at 5, 8, and 10 eV that are ultraviolet that we cannot see. So if this is a continuous spectrum like a hot object, this here is a, we'll say, electrified gas. Like a neon lamp. So I want to ask you all a couple questions now. I want to ask about a few other sorts of spectra. There's a conversation going on in the Twitch chat right now. One person has said, this is stuff I'm more used to dealing with. It's chemistry. And someone else has said, I'm the opposite. I'm better at the physics stuff and less familiar with the chemistry. This is why we're working in groups. And this is why science is done in groups. This is why, for instance, that fantastic picture of the black hole, we needed an imaging expert and a computer scientist and electrical engineers and astronomers and all of these different disciplines to work together to figure out what's going on. And if some of you have experience that is different than other people, that's normal. That means you can benefit from each other's experience. So, what might produce a spectrum like this? What sort of object? Is it the sun? Is it something that I might have on my table? Is it my chalk-covered hands? An electrified something else, right? Some other gas. So, yeah, and as Twitch chat has said, the way you know is these are narrow lines. But this is not what we have, right? Remember, we're trying to understand the sun. And the sun has given us a weird sort of combination. So remember, the spectrum from the sun looks like this. It's all of the colors with a few of them missing. We go to orange. We go to yellow. And we go to green. Take me just a minute to scribble this in, right? And blue, up at the very shortest wavelengths. one more blue that's a little more purple. So the sun kind of looks like this, except there are colors missing, right? So the sun my apologies that my eraser is a bit smudgy. But if you remember, it produces all of the colors, but with a few of them missing. So where'd the missing colors go? And Porpoise has said this is an absorption spectrum, right? The absorb means to take away. So something has absorbed these colors. So one plausible model for the sun then is that we have a hot object. We have something that has taken away these colors, and then this is what's left. So can you learn anything about where these lines are? Porpoise has said, maybe these are the absorption lines that come from our atmosphere. So if, say, Syracusium was in our atmosphere, the Syracusium in our atmosphere might absorb that line and this line. There's only so many colors of chalk I have. And whatever this gas is might be responsible for absorbing that line and that line. And then these two that are the different shades of green. Yeah, exactly. That's what's happening. Gases that are between the hot object and the Earth take away these colors. But what's between the hot object and the Earth? What objects lie between the Earth and the hot core of the sun? So Porpoise has said it's nitrogen from Earth's atmosphere. Yes. But it's not just Earth's atmosphere, because the sun also has an atmosphere. So what we see here, and we're going to talk way more about this on Sunday, what we see here, this is not just the absorption spectrum of Earth's atmosphere, this is the absorption spectrum of the sun's atmosphere. And all of these lines these are the absorption lines of Earth plus the sun's atmospheres. Because when we get above Earth's atmosphere, we still see them. And we can, using these tubes, fingerprint all of the chemicals we have here on Earth. So, what's the punchline? What's the whole point? It's that this spectrum of the sun tells us what is in the sun. And Porpoise has said, could we determine the absorption of Earth's atmosphere and then, like, canceling those things out, determine the composition of the sun's atmosphere? Yes, you can do that. That's what's so cool. This picture the one that we, let me go back to my slides here. The picture that I keep on showing again and again and again, yeah, we don't need my face here. The one that I keep showing again and again and again tells you what's in the sun. This is not just a map of the light from the sun, this is a map of the chemistry of the sun. And when we look at these lines, I want to leave you with one last thought. We've got 2 minutes left, and we have a really cool punchline in these 2 minutes. So when we look at the sun, we see all of these lines. And every one of those lines matches a chemical we know from Earth. So I know, for instance, that these two yellow ones, and I just pointed out a frame, these two yellow ones are sodium. The red one up top, I believe, is hydrogen, but many of them are iron and magnesium and calcium. And when we get above Earth's atmosphere, we still see ones for oxygen and nitrogen. So this is a map of what chemicals are in the sun. And every single one of them, when astronomers saw this, they asked the chemists. And every single one of these lines shows up in some chemical element on Earth. Except for just a few. I want to ask you all to stay 1 or 2 minutes after, because this is something you won't get from the recording next week, or on Sunday. There are a few lines here that we do not see on Earth, or we didn't see in the 1800s. So, if you see some lines in the sun that we don't see on Earth, what does that mean? What does it mean that the sun has absorption lines that the chemists on Earth have not found? Is there something wrong with the sun? Is there something wrong with chemists? Let you all think about that one. So we're out of time. Again, we have class on Sunday, but either you should make sure you listen to the recording, watch the recording, or come to the 12:30 class. San Clemente has figured it out. Ben Chernoff has figured it out. There are elements on the sun that don't exist on Earth. Yes, the chemists said, oh, we've discovered some new elements. They exist only in the sun. So if you were doing that, you would call those elements sunium, right? You have discovered a new element called sunium. And that is in fact exactly what happened. People said, oh, there are new lines. New element, we'll call it sunium. I'd like you to all go research sunium. Find it on the periodic table for me. So thank you all. Ethan has it. Ethan gave us the spoiler. Helium. Helios is Greek for sun. So they named it sunium, but not in English. They named it sunium in Greek, because the word helios means the sun. This is the story of the discovery of helium, and then a little bit later, helium was discovered here on Earth as well. But it was discovered in this picture before it was discovered here on Earth. So yeah, Liz, that's the story of helium. I'll be hanging around for a little bit to answer questions, as I always do after class. Otherwise, I've got my discussion hour.